We are just going to be looking at the final part of section 6.3. We've looked at particular word problems having to do with constraints and systems. Now we're just going to look at a specific problem that's not a word problem. It says without representing the solution set on a coordinate plane. So we're not going to represent this system here, which has two inequalities. We're not going to represent that on a coordinate plane, although we could. We are going to determine if each point is a possible solution to the system. So the way that we do that without graphing, if you were to graph it, you'd see where they overlap and if that point is in the solution region. Without doing that, what you could do is you take the coordinates, so in this point, the coordinate 0, 0, and we substitute it. Substitute 0 in for x, and for y we substitute in 0 as well, and we see if it meets both both linear inequalities here. So we're seeing if is 3 times 0 minus 6 times 0 less than 18, and is 0 greater than or equal to negative 3. So substituting into both inequalities. If the answer to both of the inequalities is yes, then that point 0, 0 is in the solution region. So for the first one, is 0 minus 0 less than 18? The answer is yes. Is 0 greater than or equal to negative 3? The answer is yes. So as a result of this both being yes, it is a solution. Let's do another one. So this next one, the coordinate is negative 4 and positive 3. So if we substitute negative 4 in for x and positive 3 in for y, for the first inequality, we'd say is 3 times negative 4 minus 3 times 3 less than 18, and also is negative 4 greater than or equal to negative 3. Okay, so for the first one, it's negative 12 minus 9 less than 18, or in other words, is negative 21 less than 18. That answer is yes. For the second one, negative 4 is not greater than negative 3. It's actually less than negative 3. So the answer is no. So because one of them is a no, it is not a solution. For the final one, just before we get into the key ideas, the issue here, we don't even need to substitute. If you focus on this part here, it has to do with restrictions. What I'm highlighting in pink, that I there means that only integers in the solution region are solutions, and these are not integers. So although this seems like an easy concept, it's typically overlooked, those restrictions. So what that means is it's not a solution. Okay? So finally, the key ideas for this particular section, the key ideas for 6.3. So if you're doing word problems, which you did in the first two lessons of this particular section, for word problems, what you're going to do is define the variables. So what do the variables represent? Is it mainsail and jib? Is it bow riders? Is it fiberglass boats? And label the axes. Step 2 for word problems, what you want to do is, or the far easier way, if you could do this, is write a system of inequalities to represent the constraints of the situation. And thirdly, we graph the solution region. Once you have the system, you can graph each of the boundary lines and shade each of the sides, etc. So we want to keep in mind the following. First of all, we want to keep in mind, are the boundaries solid or dotted? So just things to keep in mind as you're graphing the system. Secondly, is use a test point to determine which side of the boundaries to shade. And thirdly, consider the restrictions for the solution region. So basically, are you restricted to only positive integers, which are whole numbers? Are you restricted to just integers? Or can you have any number or all real numbers? Okay. Next, or important, if you can't do step 2, which is actually the critical part and it makes it a lot easier, if you don't know how to write the system of inequalities, there is a way to still solve these. So if you can't do that step, you could graph the boundary line from the word problem itself by removing any, what I'm going to call optimal language. So if you remove the more, less, at least, no more, maximum, minimum, all you need is 2 points. So only 2 points are needed to graph the line. I never taught it this way. I always came up with the system of inequalities. Secondly, shade the appropriate side of each boundary line by considering the optimal language. And lastly, consider any restrictions. If you're in my class, you're going to want to try this problem below on your own and get me to initial it.